Have you ever imagined a cat that is both alive and dead at the same time? Sounds impossible, right? Now picture a thought experiment, a puzzle that challenges our everyday understanding of reality. This puzzle, known as Schrödinger's cat, involves a feline, a sealed box, and a vial of poison. It's a mind-bending concept that questions the nature of existence and reality itself. So, buckle up your seatbelts, folks. Welcome to the paradoxical world of quantum physics. So who is this Schrödinger, and why did he come up with such a bizarre idea? Meet Erwin Schrödinger, the Austrian physicist, who is one of the key figures in the development of quantum mechanics. Schrödinger was a man of great intellect, but also a man with a deep sense of curiosity and perhaps a touch of mischief. He was fascinated by the strange world of quantum physics, but he was also puzzled by it. It was this mix of fascination and puzzlement that led him to propose his now famous thought experiment in 1935. The experiment goes like this. Imagine a cat, a sealed box, a Geiger counter, a radioactive substance, and a vial of poison. The cat is placed inside the box along with the Geiger counter and the radioactive substance. If the Geiger counter detects radiation, it triggers a mechanism that breaks the vial of poison, and the cat dies. Here's where things get really strange. Before the box is opened, the cat is in a state of quantum superposition. This means that it is simultaneously in two states. It is both alive and dead. This isn't just some philosophical musing, it's a fundamental principle of quantum mechanics, a theory that has been confirmed by a vast array of experiments. Now, you might be wondering, how can something be both alive and dead at the same time? That's exactly what Schrödinger was wondering too. He proposed this experiment not because he believed it was literally true, but to highlight the absurdity of some interpretations of quantum mechanics. But here's the catch. Only when the box is opened and an observation is made, does the cat's state collapse to either alive or dead. Until then, it's both. This is the crux of Schrödinger's cat, a thought experiment that continues to baffle, intrigue, and inspire discussions about the nature of reality and the role of observation in the quantum world. And so we have a cat that is both alive and dead, until we check. Now, this idea of being in two states at once is called quantum superposition. This concept may seem a bit tricky at first, but let's break it down using a simple analogy. Imagine you are flipping a coin. While it's in the air, before it lands, you can't tell if it's going to be heads or tails. It's in a superposition of states, both heads and tails at the same time. This is similar to our friend Schrödinger's cat. Before we open the box, we can't tell if the cat is alive or dead. It's in a state of superposition, both alive and dead. But here's the kicker. In the quantum world, it's not that we just don't know which state it's in. The system is literally in all possible states at once, and it stays that way until we observe it. Now let's talk about the role of observation in quantum mechanics. You see, in our everyday world, we can observe a coin in mid-air without affecting its state. But in the quantum world, things work a bit differently. When we observe a quantum system, we're not just passively watching. Our observation interacts with the system and forces it out of its superposition. It's like the universe is saying, all right, you've looked, now I have to decide. This is what we call the collapse of the wave function. It's as if the universe randomly picks one of the possible states for the system to be in. So when we finally open Schrödinger's box, the universe decides if the cat is alive or dead. And until we look, it stays in its fuzzy state of being both. So, in the quantum world, observing changes everything. Our act of looking, of observing, is what determines the state of the system. It's a wild idea, but that's the beauty of quantum mechanics. It challenges our everyday intuition and invites us into a world where cats can be both alive and dead, and coins can be both heads and tails, until we decide to look. But what does this really mean? And why should we care? You might ask. Well, Schrödinger's cat is not just about a feline in a box. It's a metaphorical gateway to understanding the philosophical implications of quantum mechanics. Let's delve into this realm of thought. The cat, simultaneously alive and dead, represents the state of superposition in quantum theory. This state persists until an observation is made, causing the wave function to collapse. But what does this observation entail? Does it require a conscious observer? Or can it be any interaction with the environment? These questions lead us into the philosophical territory of quantum mechanics, wrestling with the nature of reality and the role of the observer. Now, let's introduce some interpretations of quantum mechanics that attempt to explain this conundrum. First, we have the Copenhagen interpretation. It suggests that the act of measurement forces the quantum system to collapse into one state. In our case, the cat is neither dead nor alive until we open the box and look. Next up, the many worlds interpretation. It proposes that all possible outcomes of quantum measurements are realized in some world or universe. So, in an alternate universe, our cat could be alive, while in another, it might be dead. It's a mind-bending concept, isn't it? And these are just two of many interpretations. Each offers a unique perspective on the paradoxical behavior of subatomic particles, sparking ongoing debates in the scientific community. So, why does any of this matter? Why should we care about a theoretical cat in a box? Because it's not really about the cat. It's about the fundamental nature of the universe. The discussions around Schrödinger's cat challenge our classical intuition, pushing us to think differently about the world and our place in it. They open up a vast field of possibilities, where our understanding of reality is constantly tested and redefined. The implications of this thought experiment extend beyond science. They permeate into philosophy, into theology, even into our everyday lives. They make us question our perception of reality and the influence of our observations. They encourage us to grapple with uncertainty, to embrace the complexity of the universe, and to keep seeking answers, no matter how elusive they might be. As you can see, Schrödinger's cat opens a Pandora's box of questions. It's a fascinating journey into the world of quantum mechanics, where nothing is as it seems, and everything is a realm of possibilities. But wait a minute, we don't see cats that are both alive and dead in our everyday life, do we? Now, this is where the plot thickens. The principles of quantum mechanics, as peculiar as they might seem, don't appear to apply to the macroscopic world we live in. But why is that so? The answer lies in a concept known as decoherence. In the quantum world, particles can exist in multiple states at once, thanks to superposition. But in the real world, things are different. When a quantum system interacts with the environment, it rapidly loses its quantum properties, a process known as decoherence. This essentially forces the particle to choose one state over the others. Now imagine our Schrödinger's cat, in its box, experiencing the hustle and bustle of the world outside. The box isn't isolated from the environment, so the cat, the poison, the Geiger counter, they're all constantly interacting with the environment. This interaction causes the cat to decohere, to pick a reality where it's either alive or dead, not both. But where exactly is the boundary between the quantum and classical worlds? This is one of the biggest questions in quantum physics, and we don't yet have a definitive answer. Some believe it's a matter of size. Particles are quantum, cats are not. Others argue that it's about complexity. A single particle can stay quantum, but a complex system like a cat can't. There's also the argument that there's no sharp boundary at all. Instead, the transition from quantum to classical is gradual and depends on how much a system interacts with its environment. This is known as the quantum to classical transition, and it's a hot topic in modern physics. So, while we don't have quantum cats, the principles behind Schrödinger's cat are very much real. The peculiarities of the quantum world may seem far removed from our everyday experiences, but they're at play in every moment, in every particle. And as we dig deeper into the mysteries of the universe, who knows what other quantum surprises await us? In the end, what can we learn from this thought experiment? Well, Schrödinger's cat serves as a powerful metaphor, illustrating the counterintuitive principles of quantum mechanics. It brings to light the concept of quantum superposition, the idea that a quantum system can exist in multiple states simultaneously until observed. This thought experiment also underscores the critical role of observation in quantum mechanics, suggesting that the act of observing can indeed influence the state of the system. It challenges our classical intuition and pushes us to think beyond our everyday experiences, hinting at a reality that is fundamentally probabilistic. The philosophical implications are profound too, sparking debates on the nature of reality and the relationship between the observer and the observed. While it remains a theoretical construct, not something we can literally perform, Schrödinger's cat is a compelling reminder of the enigmatic and complex world of quantum physics. And so Schrödinger's cat continues to challenge our understanding of the world, one quantum leap at a time.